want to talk about something called the derivative. Now, for each of these problems, I could use the difference quotient, but that's a little tedious. There's a quicker method, and it's called the power rule. Now, you can't always use the power rule, but when you can, you want to implement it. Basically, all you do is you take that exponent and multiply it by the coefficient in front. So 5 times 3, that will give me 15. And then you subtract 1 from that exponent. So that'll give me 15x to the 4th. And a way of saying that you've taken the derivative is not y to the 1st, that's y prime equals 15x to the 4th. And that's pretty quick. Yeah, you just found the derivative of 3x to the 5th. Now I want to find the derivative of 3x to the 5th plus 2x cubed plus 4. Now this is a little theoretical. Technically that's 4x to the 0 power. Because from algebra we should all remember that anything to the 0 power equals 1. And that's why when you take the derivative of just the number 4 or 75, it's going to equal 0. So the derivative is 5 times 3, that's 15x, and then I subtract 1 to the 4th, plus 3 times 2, that's 6x, don't forget to subtract 1, squared. Now 0 times 4 is 0. Another way to say that you've taken the derivative of this is to say dy dx. But it's just quicker to put y prime. Now this one's a little bit more involved. We can implement something called the quotient rule because these are quotients, they're fractions, or we can play around with the exponent in order to make it quicker to find the derivative by using the power rule. So I want to rewrite this, not y prime, y equals x to the negative 2. Remember, laws of exponents state if I bring him back up, his attitude, his exponent is going to change to negative. Plus x to the negative 12th. Again, I brought this x to the 12th upstairs, and when I do, the exponent changes. Now, 3x to the 5th, we've been finding the derivative of that. It stays the same. It's not a fraction. So I'm going to say y prime equals negative 2x to the negative 3rd, because I have to minus 1 from the exponent. Negative 12 times 1 is negative 12x minus 1 to the negative 13, plus 5 times 3 is 15, x minus 1 to the 4th. Now, some people wish for you to rewrite this without any negative exponents. So what you might want to do is the negative 2 stays upstairs, and the x to the negative 3 goes on the bottom, and when it goes downstairs, its exponent changes to positive. Minus 12 over x to the 13th plus 15x to the 4th. To find the derivative of this expression, it's not a polynomial expression because I have negative exponents and radicals. It's very difficult to use the power rule on a radical, so what you'd like to do is change that radical form into a rational exponent. I have a cute little story that goes with this. That's a bucket, and since the 3 is in the bucket, the 3 goes on the bottom, and then the 2 will go on the top. Plus, well, this guy's downstairs. This is 1 over x to the 4th, so I'm going to bring that upstairs, and when I bring it to the numerator, his exponent changes to negative. And then add 3x to the 4th. Now I'm ready to differentiate this or find the derivative of this expression. So the derivative will equal, that's not y to the 1st, that's y prime, equals, well, I do 2/3 times the number 1 out front. So that's going to give me 2/3 x. And don't forget I have to minus 1. But a little trick is to write 1 as 3 over 3. And that will give me a common denominator. So that's going to give me to the negative 1/3 power. The exponent using the power rule times the hidden 1 up front. That's going to give me negative 4x. Don't forget I subtract 1 to the negative 5th plus 12x minus 1 to the 3rd. Now, in some schools of thought, they don't like negative exponents. So what we're going to do, just in case, if you're required to, is change these negative exponents to positive exponents. So the 2 is on top, so he can stay there. 2 over 3, x to the 1/3, minus 4 over x to the 5th. If you write this as a fraction, the x to the 5th is next to the negative 5th, goes to the bottom, plus 12x cubed. Now, a lot of times you'll be done with the 2 over 3x to the 1/3, 4 over x to the 5th, but some schools of thought don't like you having a rational exponent. So dy dx equals 2 over 3. Now what's in the bottom is a 3, so that goes in my bucket. X, and I don't need to put the 1 there, but I will. Minus 4 over x to the 5th plus 12x cubed. It depends on who you're working with, where they allow you to stop. Some schools allow you to stop there. Some make you go to this step. And then in really extreme cases, they'll make you rationalize or unrationalize, whatever you want to call it, everything to get it to look like that. What I do is find derivatives of trigonometric functions. So the derivative of y equals sine x, and most teachers or professors expect you to commit this to memory, but there's usually somewhere in the book a list of derivatives. So you can seek through this and then, oh, there it is. The derivative of sine x is just cosine x. So I shouldn't put equals there. I'll put y prime, I'll put like a hyphen, semicolon. Y prime equals cosine x. So by logic, y prime, the derivative of cosine, you think would be sine x, but it's not. It's not. If you look at the derivative table, it's actually negative sine x. Sometimes you get confused and you forget which one's positive or negative. Derivative of tangent x, well, again, I'm going to go to my list of derivatives, and that's actually secant squared x. So y prime, the derivative is secant squared x. The derivative of 5 sine x, well, is going to be 5 cosine x. So that's going to give us y prime equals 5 cosine x. And the derivative of 8 cosine x, or the derivative of cosine x, was negative sine x. So that's going to give me the derivative y prime equals negative 8 sine x. Now, in order to do this one, you have to realize that sine x squared equals sine x times sine x. It's not the same as saying sine x squared. No. It's the same as saying sine x squared. So in order to find this derivative, I'm going to have to use something called the product rule. To use the product rule, after you've split this into a sine x times sine x, you want to label this first part as something called u, and the second part as v. I split it down the middle, and I have two elements. I'm multiplying sine x times sine x. That's where the word product rule comes into play. Now, product rule is right here. If you're multiplying two elements, it's u dv plus v du. So I'm going to write that down. U, the first element, times the derivative of the second element, plus v, the second element, times the derivative of the first element. And I have a little graphical organizer that I implement for this. I put u equals here, v equals here, the derivative of u equals here, and the derivative of v equals here. Now, u is just sine x, and v is sine x. Kind of strange. The derivative of u is, or the derivative of sine x is cosine x, and the derivative of sine x is cosine x. Now I have to do u times derivative of v, so I do sine x times cosine x. Sine x times cosine x plus v du. That's going to give me sine x times cosine x. And since I have two of the same terms, like terms, I'm going to combine like terms. That should give me dy, the derivative, dx equals 2 sine x cosine x. And that's my final answer, using the product rule. Find this trig derivative by using something called the chain rule. For number 6, I used something called the product rule, and I rewrote the trig function as cosine x times cosine x. That's how I did this process in number 6. But now I want to rewrite it like this, as y equals the quantity cosine x squared. That means cosine x times cosine x. Now I'm going to use something called the chain rule. And the chain rule is sort of the product rule, but with a little extra touch. And here's the deal. After I take the derivative of this big quantity by doing the power rule, 2 times the hidden 1 up front. So that's going to give me y prime equals 2 times the hidden 1 up front. That's 2 times that quantity, cosine x. Don't forget the minus 1 to the first power, but I don't need to write that. After I do that, then I have to take the derivative of the guts. And the derivative of cosine x, I believe, is negative sine x. And I'm not quite done. I'm going to spruce this up a little bit. So the fancy looking derivative, dy dx, is actually negative 2 cosine x sine x.